Thank you for joining us today. My name is Allison Van, and I'm the Executive Director of SPARC, a Center for Social Research Innovation. Welcome to today's SPARC Talk, Handling Missing Data in Social Science Studies. I'd like us to begin by giving honor and thanks to the Haudenosaunee and Anishinaabe nations as the traditional inhabitants of the lands where McMaster stands. To say that is to acknowledge a debt to those who were here before us and to recognize our responsibility to respect and honor the intimate relationship that Indigenous peoples have to this land. We're thrilled today to welcome Rod Little, who is the Richard D. Remington Distinguished University Professor of Biostatistics at University of Michigan, where he also holds appointments in the Department of Statistics and the Institute for Social Research. And we are excited to be hearing today about approaches to handling missing data. So thank you, Rod, and take it away.
Okay, thanks, Allison. Thanks for inviting me. Thanks, everybody, for coming. I'm going to share my screen, so hopefully everybody will see it. I don't really want to see this. Disable about high video panel. Does that do me? I don't quite know how to hide this panel. Floating meeting control. Yes, that's it. Okay, so what I'm going to do, no, I'll get it right, actually. Okay. So I'm going to give an overview of missing data methods and have quite a lot to cover, and I'll try and I deliberately try to cover a lot of material fairly quickly. I apologize if I go too fast. I will make the slides available, and if you want to ask me a question, then feel free to pipe in, or you could send something on chat. So I'm going to first have a little bit of a preliminary discussion. First, I'll actually define what I mean by missing data. It might seem like a bit of an obvious thing, but it's not always as obvious as you might think. And then talk a bit about missingness mechanisms, reasons why you have missing data, whether it's related to the variables in the data set. Any method you have for handling missing data makes some assumptions about missingness. And so this is a crucial theoretical issue that underlies a lot of missing data methods. I'll also talk a bit about the properties of a good method for handling missing data. Then I have main approaches to the analysis of missing data. I'll talk about maximum likelihood, Bayesian methods, also complete case analysis and weighting, and some of the material. I wrote a paper with Carpenter and Lee that I think somebody looked at, which is why they were interested in me giving a talk. So this touches on some of the material in that paper. Multiple imputation, which I think is one of my preferred approaches to handling missing data. A little bit about robust type of approaches that don't make such strong distributional assumptions. And then strategies for handling missing not at random, a term which I'll define a little bit earlier in the talk. There are a bunch of textbooks. I have the book with Don Rubin's Statistical Analysis of Missing Data. I'm very proud of this cover because I designed it a long time ago. This is now in its third edition. There's a bunch of other books that are good that I like. Rubin's Multiple Imputation book in 1987. Joe Sapler has an important early book, and then a bunch of other folks here have nice books, including my colleague Raghunathan at Michigan, and we do a lot of short courses together. And he's done some excellent work on developing multiple imputation. And then I mentioned the Lee Carpenter paper that's in the references. And I have a review paper coming out in the psychology, annual reviews in clinical psychology that I used for some of these slides. So we have a data matrix here. The rows are cases or observations, the columns are variables. And the gaps here are supposed to represent missing values. So this is a kind of a general pattern of missing data. There's missing values strewn across the data matrix. Sometimes we call that a Swiss cheese pattern. Just holes in the Swiss cheese. So what is missing data? How we define it? The way I like to define it is, if I was to fill in those gaps, would they be meaningful for analysis? So if they are meaningful, then it's missing data. If they're not meaningful, then to my mind, it's not missing data. So missing data are unobserved values that would be meaningful for analysis or observed. Couple of examples. So if you have a clinical study, somebody misses a clinical visit, then the recordings that they would have got from that clinical visit would presumably be meaningful for analysis. So that would be an example of missing data. If unfortunately they didn't show up because they died, and you were doing a study on quality of life, for example, then that's not missing data from my point of view, because I don't think it makes much point to talk about quality of life for people who are not alive. But in any particular situation, it's worth sort of thinking, I think, about whether this really is missing data or whether we should just exclude those cases from the analysis. I talked about a general pattern of missing data, which is sitting in D in this picture, figure 1. There are special patterns of missing data. In particular, first one, A, is just missing data on a single variable, or in B, on a block of variables with the same pattern. That happens in, for example, unit non-response in surveys. A monotone pattern, where as you go across the data, you get more and more missing values. That arises, for example, with attrition in a longitudinal study. And then a general pattern. The last one, E, is what I call file matching. So we're often interested in combining data across data sets. And then you have some variables that might be common to both of the data sets, and a set of, that's Y1 here, a set of other variables that are at Y2 in one study and Y3 in the other study. So that gives you a pattern that looks a bit like that. And there are certain parameters, and you might not be able to estimate parameters of conditional association between Y2 and Y3 given Y1. There's really no information in that pattern, and we have to bear that in mind. With missing data, there's also a possibility that some things that you can estimate with complete data don't aren't estimable simply because variables are never observed together. Then there's the mechanism. So why do we have missing data? In particular, is it related to the study variables? That's really the important question. There's some famous terminology that goes back to Rubin's 1976 paper. D is a data matrix. D0 is the observed part of D. D1 is the missing part of Z. So 1 standing for non-response here. A missing data indicator matrix taking the value 0 for items that are observed, 1 for items that are missing, and the sort of 1 minus the response indicator matrix, which is the other way around. Then Rubin defined missing completely at random if missingness doesn't depend on the values in the data. So the probability of M given D doesn't depend on D. Actually, I have this wrong. So I should remember to fix this slide. So that should be probability of M given D is the probability of M, not the probability of D. Then missing at random, meaning the distribution of M only depends on D through the observed values, D0. And that's a very important concept in missing data analysis for reasons I'll explain later. Missing not at random, missingness also depends on things that are missing. So if you have, for example, missingness of income was a variable that you're not measuring in a survey for some people because they don't want to tell you their income, then missingness of income, that depends on variables that we have observed in the data set, age or marital status or whatever we have measured, but not on the income itself, then that would be missing at random. But if it depends on the values of the income itself, then that's missing not at random, after conditioning on the variables we have observed, technically. So as I said, properties of missing data methods depend crucially on the missingness mechanism. Most of the methods you'll see in software out there assume missing at random, but is not an easy thing to test. The issue that is, in some senses, the parameters that determine whether you're missing at random or not are not identified from the data set without making some additional assumptions. So one of the tricky aspects of missing data methods is that often we assume missing at random, but we can't really tell whether that's really true or not. What's a good missing data method? Essentially makes efficient use of the available information in the data set. It should be based on plausible assumptions about the missing data, and it should provide valid statistical inferences. In other words, the inferences from the incomplete data analysis have proper good statistical properties. For example, confidence intervals that are supposed to be 95% confidence intervals should have that nominal confidence coverage in repeated sampling, or something like it, close to it. Hypothesis tests should have a close to nominal size. So one of the main issues with single imputation, which I'll mention later, is if you just fill in data and then analyze it if it's complete, then you're overestimating the amount of information you've got. So you tend to be underestimating the standard error, which would mean that confidence intervals are too narrow, which might make you feel good, but is not good from a statistical point of view. And then exploits information contained in the incomplete observations for inference about the parameters of interest. Notice that the goal here is not really to get the best estimates of the missing values. So machine learning literature, for example, focuses a lot on predictions of the missing values and getting the best estimates of them. But that's not the game I'm into here. That might be a good game in some settings, but it's not the one I'm talking about here. I'm talking about making inference about parameters that have the right statistical properties. If anybody wants to ask a question at this point, because if not, then I'll move on to the different approaches.
There's one from Grant in the chat.
Yeah, I do have one just quick. You said you can't test missing at random without assumptions. Just wondering,
Right.
and this might be obvious, but why wouldn't it be valid to just test whether for a given variable I, the missingness of that variable were predictable by whether something else were missing?
So let's suppose we have y that has missing values, and and then we have an x that's fully observed. Just a simple case. You could look at whether the distribution of x differs between respondents and non-respondents to y, right? And that's a good thing to look at, actually, in a lot of settings. But that's really testing for missing completely at random. The missing at random assumption says that after conditioning on x, does missingness depend on y? After you've conditioned on x, you really don't know whether missingness depends on y, because you only see y for the cases that are fully observed. Now, there are methods like Heckman's selectivity bias thing where there are parameters that deviate from missing at random, that measure deviations from missing at random. And there are tests for those parameters within the Heckman model. That's a situation where people do test for missing not at random. On the other hand, the Heckman model really can't be fitted without making some other assumptions about which variables are included in the regression for missingness or the regression for the outcome. Okay, so let me talk about general strategies. So at the top, I have a matrix with a set of complete cases and then some incomplete cases. And I've separated them out into three different approaches. The middle one, going down the middle arrow here, is complete case analysis. So with complete case analysis, we just discard the incomplete cases and we analyze the cases that are complete. A slight elaboration of that, which I'll talk about, is weighted complete case analysis, where we calculate non-response weights and weight the cases by those estimated non-response weights. Common method that's used for unit non-response in surveys. But you're still essentially, the information is still really confined to the complete cases. The only use of the incomplete cases there is to try and make them look more representative by differentially weighting them. Then there's imputation, which is on the left, the way I'm looking at my slides, where you fill in the missing information with predictions or draws from some predictive distribution or whatever, best estimates maybe. Then there's single imputation, where you just do one and then analyze that. You have to be worried about getting the standard error right if you do that. I'm going to advocate multiple imputation, which I think is better than single imputation, because it gives you a way of propagating the error from the imputations and getting valid inferences. On the right, we have analyze incomplete. So here, there are some methods that don't require that we have a rectangular data matrix. So maximum likelihood, for example, you can calculate a likelihood function based on the observed variables, the observed data, if you like. So you don't really have to fill anything in. You can just use the information you've got. Then if you want to add a prior distribution, then you can do a Bayesian analysis as well. That's the strategy I'm going to talk about first, actually, because it's quite common in the social science literature. And there are links between these things. For example, the EM algorithm, which is an algorithm for calculating maximum likelihood estimates, does involve filling in information at some level. So there are relationships between these two things. But conceptually, I tend to think of these three approaches as being somewhat distinct. Okay. We probably know something already about maximum likelihood. So there's a statistical model, and you throw data at it, and then the likelihood is basically the density of the data treated as a function of the parameters. And then maximum likelihood estimates maximize that likelihood function. And then there's large sample standard errors based on the information matrix or bootstrap, something like that. We can do the same thing with incomplete data. So we can have a model and then take the incomplete data and formulate an incomplete data likelihood. It's more complicated than complete data likelihood, but anyway, we can still compute it and then proceed to do maximum likelihood or add a prior distribution and do Bayesian statistics. If you have missing data, though, in general, you need a model for the data without missing values, and we need a model for the missingness mechanism as well. Missingness mechanism, typically you might have a model for D, which was the whole data set, and then the model for M given D is the model for the missingness mechanism. However, it's not very easy to model the missingness mechanism. We don't know how to do it very well, and results are sensitive to getting it right. And so it would be much more convenient if we could get away with not including the missingness mechanism in the model. And it turns out that if the data are missing at random, that is, missingness only depends on the observed variables and not on the missing variables, then the likelihood based on that ignores the missingness mechanism, basically based on the marginal distribution of D, gives you valid inferences. There's also a distinctness condition that Remington talks about in the 76 paper, but missing at random is really the more important of the two conditions in practice. Most of the software for doing maximum likelihood day, for that matter, with missing data, assumes missing at random. So it assumes missing because it's not modeling the missingness mechanism. So that's a key point, which is why missing at random is such an important condition in practice. Then maximum likelihood estimates from missing data have the nice properties of maximum likelihood. That is, they have consistent estimates under well-specified models and also efficient estimates, at least in large samples. You have to worry a bit about whether parameters are identified because, as I said, it's possible, for example, in that file matching problem, some of the parameters can't be estimated, so you have a lack of identification. You can get standard errors from the observed or expected information, or the sandwich estimator, which is a more robust estimate of the covariance matrix, or the bootstrap, which has similar properties to the sandwich estimator. You can build this likelihood function. There are three sort of general approaches to likelihood-based analysis. There's maximum likelihood, which generally has these nice properties, but they're large sample properties that really assume you have a large data set. And Bayesian inference, where you had a prior distribution and compute the posterior distribution. And that has advantages when you have small samples, particularly. In large samples, I view maximum likelihood as being a form of large sample Bayes. So it's, in some senses, it's the Bayes, but you don't have to worry about the prior because you get swamped by the data. If you have small samples, then the prior tends to matter. But Bayes tends to give you better inferences from the maximum likelihood. So in my view, maximum likelihood is marvelous, but Bayes is better. Then there's multiple imputation, and multiple imputation was developed from Bayesian ideas. And in fact, you can think of it as a simulation approximation to the Bayes, And that actually has some advantages over both maximal likelihood and Bayes, which I'll mention later. In social sciences, I guess there's repeated measures models where maximal likelihood is extensively used, going back to the days of SAS, prop mixed. I actually go back to the days of BMDP, because I was in LA early in the 80s. And BMDP had a very good repeated measures program before SAS did, so I should speak up for them. Anyway, SAS or other statistical programs also have repeated measures models that are very useful. And you can calculate maximum likelihood estimates when you have missing data in the repeated measures. It doesn't actually work for repeated measures in the covariates, the baseline variables. For that, you need to do something like multiple imputation to deal with missingness there. And there are extensions to generalized linear mixed models for non-normal data. And social sciences M+ is a popular structural equation modeling program that also deals with missing data. I also mentioned Rabe Hetzkes and Kron-Skrondel have a book that talks about extensions to multi-level latent factor models, and they have software that's mentioned as part of their book. So these methods are used quite a bit in the social sciences. They're useful, certainly useful. Limited to some degree because they assume missing at random, and also they, to some extent, assume you have large sample sizes. Then there are Bayesian methods which became computationally feasible using Markov chain Monte Carlo methods like the Gibbs sampler. There's a classic paper by Tanner and Wong in JASA in the 1980s that takes the multivariate normal problem with missing data, assumes missing at random, but then shows how to generate draws from the posterior distribution of the parameters. And that was a very interesting early use of the Gibbs sampler to a really important applied problem. They call it data augmentation, actually, but data augmentation is very similar to the Gibbs sampler. Then the posterior distribution then gives you the estimates of precision without computing the information matrix. I mentioned EAM, I'm not going to talk about EAM. EAM is a very handy algorithm for calculating maximum likelihood estimates. It's not so good for calculating the standard errors. It doesn't give you the standard errors because it doesn't compute an information matrix. Bayes is actually better, from my point of view, because not only can it deal with small samples, but it also gives you estimates of precision through the posterior distribution. And a lot of existing Bayesian software packages can be used for doing inference, Bayesian inference with incomplete data, most of them assuming missing at random. So Enders, who's a psychologist, in a review paper describes Bayesian analysis as an attractive direct estimation competitor to ML. And as I said, I think maximum likelihood is marvelous, but Bayes is better. Maximum likelihood is a form of large sample Bayes. The prior distribution, far from being a weakness, to me is a strength because it adds flexibility, I think, to situations like regression when you have a lot of covariates, where things like ridge regression, which are essentially Bayesian methods, do better than, say, least squares. And then a posterior distribution giving you estimates for uncertainty that don't necessarily assume large samples, so you get T corrections and things like that from the posterior distribution. Okay, so those are methods that don't fill in the data set. So I'm now going to go to complete case analysis and multiple imputation, which are two methods that create rectangular data sets. So first I'm going to talk a bit about complete case analysis, where you just discard the information in the incomplete cases and just analyze the complete cases. Often this is a default option in a lot of analyses. Is it terrible? In the literature, complete case analysis is given a hard time, I have to say, including by myself. But actually, there are some situations where complete case analysis is, to my mind, perfectly okay. And that is when the information in the incomplete cases is very small. So if there's not much juice to be extracted from the incomplete cases, it's probably not worth going to a lot of trouble trying to fill them in or use them in some ways. Trouble is, what's small here is a little bit of a complicated issue because it depends on the fraction of incomplete cases, obviously. Also depends on what the information is that's recorded in these cases. Is it significant for the thing I'm interested in? And then what am I actually estimating? So it's not an easy thing to necessarily say, although obviously if only you have 1% of the cases have missing values, that's probably not much information there, but in other settings it's maybe less clear. Loss of information here may lead to inefficient estimates because you're throwing things away, but also bias because the complete cases may not be representative of the cases you started with. I have a couple of examples here. This is a situation where you have missing data on a variable y, and then you have a set of x's that are fully observed. And let's just suppose that this set of x's collectively give you a strong predictors of y. So if we were to do a regression, the R squared between y and these x's would be high, so 0.8 or 0.9. If I'm interested in the mean of y, it's intuitively reasonable, I think, that the incomplete cases might carry quite a bit of information about the mean of y because we have good predictors of y for each of the incomplete cases. On the other hand, if the x's are not very strong predictors of y, so if the R squareds, all R squareds in social sciences are 0.2, isn't that right? Isn't that the rule of thumb? So if R squared's very small here, then maybe they don't help you a whole lot. On the other hand, if we're interested in the regression of y on the x's, not the mean, but the conditional mean of y given the x's, then under missing at random at least, there's no information in the incomplete cases at all, whether the predictors are strong or weak. Essentially, you have to have something that's correlated with y after conditioning on x1 up to xp. So that would be a situation where with missing outcomes y, where imputation doesn't do you any good because essentially there's no information to recover from the incomplete cases. Now, if you have a general missing data pattern, complete case analysis is missing. It actually gives you valid estimates, at least under a well-specified model, if missingness depends on the covariates, but not on the outcome, which could actually be a missing not at random mechanism. So if missingness depends on the covariates, a covariate that's sometimes missing, then that's missing not at random, but the regression based on the complete cases is still valid, providing missingness doesn't depend on the outcome. So this is just to illustrate this is not a particularly straightforward issue. Actually, from a practical point of view, I don't really object to doing a complete case analysis and doing something like multiple imputation and just seeing how much difference it makes. Oh, I should skip over this. So I was talking to this educational conference, and some of you might be interested in this, what works, remember what the C stands for. This is in education, so I was talking about that. I had too many slides here, so I was going to throw these out anyway. So, okay, all right, I'm going to skip over that. Going to imputation of this. So when is imputation useful? So imputation of the outcome is justified when there are auxiliary variables, other than x1 to xp that I talked about, that are observed and not included in the final analysis. And one example of that might be repeated measures data, where you have an outcome that's the change from baseline to time t, and you have some variables y that are measured before time t, but not at time t. Those cases might be useful because those intermediate values of y are then auxiliary variables. Then if you don't assume missing at random, there's various missing not at random methods that you could apply that do include the incomplete cases. Skip over this. Oh, I'm going the wrong way. Oops, sorry. Okay, that's a bit about complete case analysis. Then weighted analysis. So how about weighting the complete cases to make them more representative of the original sample? This is the common method for downhanding non-responsive surveys. And in a sense, it extends the weighting ideas for sampling when you have differential sampling weights to deal with unit non-responsive surveys. The difference is that So the idea is if you have the response weight, that's the probability of responding. If you have an estimate of the probability of responding, and you have the sampling weight, which is the probability of being sampled. If you multiply them together, then you have an estimate of the probability of being sampled and responding. And the inverse of that product is then a kind of an extension of the sampling weight. The thing that's different is that in non-response, you don't know what the response weight is, whereas in sampling, you know what the sampling weight is, at least in principle you do, unless the survey sampler doesn't tell you. So you have to estimate them. And non-response weights are typically estimated using a simple method we call adjustment cell weighting, where you classify responders and non-responders into adjustment cells based on variables that are fully observed. And then you weight by the inverse of the response rate in each cell. So all the units that are sampled, that are respondents in that cell, get weighted by the inverse of the response rate. Then you would rescale the weight to sum to the respondent sample size. That gives you something that's closer in terms of standard errors. More generally, you can deal with continuous variables that are fully observed by doing a regression of the indicator for response, the M, on the observed variables, doing something like logistic regressions into binary outcome, and then weight by the inverse of the estimated propensity to respond. That's a sort of more general idea that the adjustment cell weighting can be seen as a special case of response propensity weighting. The thing I want to say about this is that for these methods really to work, the observed covariates, the variables we have observed for respondents and non-responders, must be good predictors of the survey variables of interest. In fact, if they're good predictors of non-response, but they're poor predictors of the thing you're interested in, the why, then weighting just makes things worse because it doesn't help you for bias and it just adds variance. One of the problems with non-response weighting, from my point of view, is a lot of cases, the variables you actually have observed for everybody as demographic variables that might be relatively weakly related to the thing you're interested in. And in that situation, survey samplers typically weight, but it doesn't necessarily do them much good. Often it'll just add noise. So if you can link or create post-stratification cells by using external information, that using variables that are closely related to the thing you're interested in, then this kind of a method can be quite useful in reducing bias. I'm leaping ahead a little bit. Post-stratification uses weights that are based on information from an external source, like a census data or large survey like the American Community Survey. Using methods like post-stratification, and for a multiple set of these things, we have a method called raking, which essentially simultaneously takes into account a bunch of variables you have measured in the whole population. There are extensions of these weighting methods. So there's augmented inverse probability weighting methods that have a model that predicts the missing values, but then weights the residuals using the non-response weight that I just mentioned. That can be better than just weighting alone. It can be more efficient. And it has a sort of double robustness property that it gives you valid estimates whether the propensity model is correct or whether the model for the variable of interest is also correct. 3. There's not so much software around for doing inverse probability weighting. And personally, I prefer multiple imputation type of methods. Essentially, I'm not a huge fan of weighting because often the weight, to my mind, just adds noise without doing very much for the bias. Another issue with weighting is that it doesn't really handle general patterns of missing data, such as item non-response in surveys. So if you have a general pattern, it's not at all clear how to define a weight. And there isn't really a weight that really incorporates all the information. So non-response really is better. The item non-response is better handled using imputation, like multiple imputation. Okay, so I'm sure some of you are a little bit familiar with multiple imputation, but the idea is that you have, instead of just filling in the data once, you fill in a bunch of times, where each filled in data set has different draws from a predictive distribution of the missing values. So you're not actually filling in the best estimate of the missing value, as you might in a machine learning game. You're filling in a draw in the predictive distribution that has this noise added. But then you do it lots of different times. So you have different draws to fill in each of these data sets. There's simple multiple imputation combining rules that give you valid inferences under well-specified models. In fact, the theory of multiple imputation is kind of Bayesian. This is a simulation type approximation to posterior distribution inference. Unlike single imputation, multiple imputation really has two very useful features. One is that it propagates the imputation uncertainty through the combining rules, and then involves averaging the estimates of the multiple imputation data sets, and that deals with the lack of efficiency from doing draws rather than best estimates. You could do multiple imputation even if you have a lot of missing data. Even if the predictive power of the models is weak, essentially because the standard error is still valid because you're propagating the imputation uncertainty. There's a little bit of a penalty from using a model to do the imputations, but provided you have a reasonable size data set, that's not necessarily a huge issue. And one of the nice advantages of, I would say, imputation and multiple imputation over sort of maximum likelihood or Bayes is that you can include auxiliary variables in the analysis model, in the imputation model, that are not included in the analysis model. An example of that is if you have variables when you're creating the data that are not available to the user, for example, because of confidentiality issues, localities and things like that, you can't give to the user because of confidentiality. Those variables can be used to create the multiple imputations, and then you hand them over to the user, and they get the benefit of the predictive power of those variables without actually having the auxiliary variables. There are other situations where it's useful to have an imputation model that differs from the analysis model. So I think this is an advantage of multiple imputation. A couple of things other advantages. One, it'll deal with the general pattern of missing data, and there's a lot of software now for doing it. So there's pretty flexible software, which I'll talk about in a minute. People tend to think that multiple imputation is useful for missing at random and not for missing not at random, but that's actually not true. You can do missing not at random models as well. And I'll talk a bit about missing not at random at the end, but it's particularly useful for a sensitivity analysis, look at deviations from missing at random. And multiple imputation is a useful tool for that kind of sensitivity analysis as well. There are three sort of general approaches to creating multiple imputations. My thesis was actually on maximum likelihood for the multivariate normal model with missing data. I was doing the EM algorithm, although I didn't know it at the time. It hadn't been invented until a bit later. So you could assume, say, a normal distribution for the variables and then create multiple imputations under that model. Typically, they would be Bayesian. So you'd have a weak prior distribution, relatively non-informative prior distribution of the parameters, and then you do draws, the posterior predictive distributions of the missing values, and then from those multiple draws, multiple imputation data sets. Then there's a method that doesn't necessarily assume a parametric model, like the hot deck. The hot deck is a method where you take observed variables and then you match the incomplete case to the complete case based on a metric of closeness from the observed variables, and then you just impute the values from the matched case to fill it in. Some advantages of that is that you're always imputing real values, which can be useful, particularly if you're doing transformations. You can get into trouble if the model's wrong. So it's a little bit less sensitive to the model. It's getting the model wrong, but it's not so good for small samples. It's better method for large samples than small samples. There's a method called predictive mean matching, where the metric is based on predictions from a regression, which I think is the best metric. And so there are other metrics like Mahalanobis distance, or just using adjustment cell type methods. But predictive mean matching is the way to go, and that's available actually in software like in SAS. Then the third approach is sequential regression or chain equation imputation. In some senses, I recommend this as being the method of choice for multiple imputation in a lot of settings. Why do I like it? The problem is that modeling the joint distribution assumes that you have that joint distribution correct. And we're not very good at specifying joint distributions. We don't have a toolkit that has a lot of joint distributions that will deal with interactions and nonlinear, different forms of nonlinearity. Sequential regression is not as theoretically justified, but it's more flexible from that point of view. So what does it do? So Raghu has a program, IVE, that does this. So he's my colleague at Michigan. And then Van Buren Utshold, that's MICE, which some of you probably are familiar with. That's multiple imputation by chain equations that's available on the internet. And it's also a good package. What does it do? It's a bit like a Gibbs sampler for those what Gibbs samplers does. So you imagine a set of conditional distributions. Each variable that has missing value, you regress on all the other variables, including the fully observed variables. So you do y1 given y2 up to yp and z, if z is fully observed. Then you do y2 given y1 and y3 up to yp and z, and so on through the data set, which is what you do in the Gibbs sampler. The thing is that each of those univariate regressions is then assigned a distribution that's appropriate. So if it's a continuous variable, you might like the normal distribution. If it's a binary variable, you might use a logistic distribution, a logit model, or if it's count data, a Poisson model, and so on. How do you regress each variable and all the other variables when all the other variables have missing values? Well, you just do this sequentially and just use the most recent imputations for the other variables that have been filled in from previous iterations. So that's like a Gibbs sample, how that operates. So it's iterative. You go around and around, and eventually you can create multiple data sets using this approach. It's very flexible. And you have to think a bit about the models for each of these variables as you go along. So you don't want to do something that's grossly inappropriate. But it has a lot of flexibility, which outweighs, to my mind, theoretical issues as to whether it really is. It's not really a Bayesian method, except in special cases. So it lacks some of the theoretical properties of a fully Bayes approach, but it's very useful from a practical point of view. I just mentioned briefly in passing, I don't know how much time I have here, not too much, but there are methods that combine. I'm now going to talk a bit about robust approaches. This is a method that combines weights that I talked about and prediction within a regression model, which I like. I told you I didn't like non-response weighting very much. I don't using the weights as the inverse of the estimated probability of response as a weight, but I do using it as a covariate. And so you can estimate the probability of response. I'm sorry, I'm using an R here rather than M, but then do a model where you regress on function of the predicted probability of response, or a logit of the predicted probability. Spline just meaning a smooth function of that estimate, and then add other variables parametrically. So this is a regression style of model, but it's non-parametric for dealing with the non-response propensity, and parametric for other variables that you might include if they're predictive of the thing you're interested in. So this is a hybrid kind of approach that I like, that deals with a weight, but as a predictor rather than as a non-response weight. Other flexible approaches, most of this game of multiple imputation, for example, is doing a bunch of regressions. And there's nothing to stop you using more modern versions of a regression rather than just doing least squares or logistics, parametric logistic regression. So you could do a ridge regression, you could do a lasso, elastic net, you can use regression trees, Bayesian additive regression trees. These are more modern kind of regression methods. And you can do that to fill in the missing values rather than doing a more strictly parametric method. So these are not quite so available in software, but I suspect they'll be coming out in the next few years. Finally, I'll say a little bit about missing not at random, which is a tricky issue. My book with Rubin, we spent quite a bit of time revising the last chapter, which talks about missing not at random and putting a little more structure on it. And essentially, we delineate here 4 different ways of dealing with situations where you might be missing not at random. One is to collect data. This is probably the best way if you can do it. Follow up a subsample of non-respondents, collect some key information, at least on the subsample, the things you really care about, and then use that information together with the respondent data that you had before, either to do imputation or to do weighting. I mentioned the Heckman model. So if you impose restrictions on the model parameters, such as the regression coefficients in the Heckman model, so if you're willing to assume that some variables are missing from the selection equation or for the model or the equation for Y, then you can identify those models. Otherwise, the Heckman model is very poorly identified and can get you into serious trouble. But that's another approach, and results tend to be sensitive to violations of the assumptions within the model. There's a little bit of literature, a little engineering, which I'm not going to go into here. There's some ways of actually doing something in between complete case analysis and multiple imputation, where you keep some cases but throw out other cases, and that can give you valid inferences on the particular missing not at random assumptions. They call that subsample ignorable likelihood methods. And then the final thing is the sensitivity analysis of clinical trial area. This is now becoming quite common, in fact, because the FDA is actually asking to show people that results are relatively robust to other assumptions about missing at random. And I like something called pattern mixture model or proxy pattern mixture analysis for doing that. I think to leave a few minutes, I'll skip over the details of this method, but essentially the idea is you have a variable Y that has missing values. You have a set of auxiliary variables, Z1 up to ZP. You want to do an adjustment for the mean of Y that looks at missing not at random as well as missing at random. And it's called proxy because you regress Y on the Z's using the complete cases to give you the best predictor of Y based on the Z's. You scale to have the same variance as the original Y's for the complete cases. And that's your proxy variable. So you have a strong proxy if that's a good predictor of Y, and you have a weak proxy if it's a poor predictor of Y. The correlation between X and X, which is this best predictor, and Y is a measure of how strong proxy it is. So you get the best variable you can based on the observed variables, and then use a pattern mixture model, which assumes a different distribution for X and Y for respondents and non-respondents, but make an assumption that missingness depends on a linear combination of X and Y. Essentially, it's a bit complicated. I don't have time to go into this much detail, but if you're interested in quick treat, then you can calculate Bayes or maximum likelihood under that model. It turns out that the maximum likelihood estimate of the mean, for example, is an extension of the regression estimate with a function G of rho here that involves the sensitivity parameter that you vary between 0 and 1. It's a very straightforward analysis that gives you some idea about deviations from missing at random, the impact of that on the mean. So I like this quite a lot. And recently with Brady West and some other colleagues in Michigan, I've been applying the same idea to deal with bias in non-random samples, selectivity bias type things. This is a little bit related to this Heckman model, but it's actually simpler to compute and has some advantages over the Heckman model. Okay, so this is a nice method. I don't really have time to go into it in much detail. That's about it. Perhaps I missed out the best way of dealing with missing data, which is a bit of a downer, but the best approach is not to have missing data. And the reason why is that missing data is a challenge for analysis. And any method you do for handling missing data involves unverifiable assumptions, including throwing out the incomplete cases. For that reason, the best way to handle missing data in your study is not to have missing data to the extent that you can by monitoring, following up on sites, for example, that have high levels of missing data and so on. I was chair of the National Research Council panel on missing data in clinical trials, and this was one of our key findings. And I have to say that perhaps the best thing that came from that study was that people were actually spending more time trying to reduce the level of missing data before you actually do any analysis. And there's no magic bullet for handling missing data. So the best magic bullet is not to have missing data. I'll skip over this. So there's a little bit at the end here on whether to do weighting or whether to do complete case analysis or whether to do multiple imputation. And that's in the little Carpenter and Lee paper that you can look up if you're interested. So I think I'll stop there. I think I'm pretty much out of time. Maybe it's time for a few questions, but I have a bunch of references here, and which I'm happy to make the slides available to anybody who wants them. So with that, I think I'll stop.
Thank you so much. We are right at time, but if people are able to stay, we'll stay for a little bit longer.
Okay.
See, Grant has a hand raised.
Okay. I have to put my cap on now since I was showing Allison that
yes,
Michigan are now the national champions, which is a big deal in the States, at least I don't know if it is Canada, but Allison's upset because she comes from University of Washington. Yes, Grant, you had a question. I can't hear you. You have to unmute.
Well, I was just asking if Washington's ever won anything. I don't know if Allison knows.
They have a good team.
Yeah, it's not some.
That's not nice.
As soon as I left, they started to fall apart.
Yeah. No, I like the Wolverines. I like the Wolverines, so it's okay. I guess my question is, because a lot of these things are really nice in theory, but then when you sit down with a data set and you start to look at the computational cost of some of these methods, they become prohibitive somewhat quickly. Can you just comment on some of the things where, because I know that the semi-parametric estimation on a big data set, if you don't have a cluster or some other way to do things like that, can often run you like way longer than are feasible.
All right, that's an interesting question. First thing I'd say is the software's a hell of a lot better than when I was a student. So there's a lot of software out there for handling missing data that there wasn't before. In particular, a lot of missing multiple imputation software that's very good these days. So that cuts down, I think in some senses, the thought that's required into developing the imputation models is probably the higher cost rather than computational costs. If you have huge data sets, maybe. In terms of semi-parametric models, multiple imputation can have an advantage there. If you don't have a lot of missing data, you don't necessarily have to get the imputation model super correct. So if you get the main features of the imputation model correct, you have the good predictors in there at some level, then there's nothing to stop you doing multiple imputation using a parametric model, but then doing the analysis with filled-in data using something that's more flexible. So that's another example, I think, where the imputation model might be different from the analysis model. Is it worth it? Depends on how much information there is in the incomplete cases. If there's not really very much information, that then might not be worth it.
And I guess then you could estimate if you did want to use a semi-parametric model to estimate the multiple imputation part, then you'd use a subset of the data because it doesn't really matter in some sense how well you do because the uncertainty carries through. Is that a fair comment?
Simply because it's too much work.
No, not about the amount of work. Just the sort of the ease of defending assumptions that you're making.
No, if I was going to do that, I'd try and use all the data. Essentially, one of the conceptual reasons why multiple imputation you might like it is that we don't like to throw stuff away. That's what statistics, we try to use everything we have. I think we should at some level try to do that. So I'm not sure if I would throw things away necessarily, although I do have this method that in some circumstances, particular types of mechanisms, there can be an advantage in throwing some stuff away, but that's enough. I don't really have time to go into that. You can look at the Little and Zhang paper, it'll be interesting. Actually, one example of the Little and Wang, that's a special case of this Little and Zhang thing, is that if you have a regression problem, you have missing data on the Y's and the X's. You can fill in everything using a multiple imputation program. But when you're doing the regression, just restrict it to cases where Y is observed. So you could throw out the cases where you're imputing Y. Because once you've imputed the X's, those cases don't give you any information. So that's actually more efficient than doing the full analysis. So that's actually an example of this strategy. Stephen, you had your hand up, so.
I do. Thank you. So I'm actually not in social sciences. I'm in health sciences and the applications to clinical or health. But in any case, for many years now, I have recommended multiple imputation methods to people who ask me about this. And I guess one of the surprising things that happened when I started recommending this is people started to ask me if it was okay to impute, say, 5 data sets, but only use one of them. And this actually is things that I see published now as well. The motivation seems to be that it's not always clear, or for whatever reason, it's inconvenient or difficult for a particular estimate to know what the rule is to combine things, perhaps for example, fits of statistics in a latent variable model or something where the rule might not be clear. I'm wondering if the imputation errors generally are small, the bit that propagates into the final confidence interval, for example, what would you say to that sort of procedure?
It throws out, to me, the two advantages of multiple imputation.
Yeah.
One advantage is the gain in efficiency from averaging over the data sets. The other is getting appropriate standard errors. If you use a multiple imputation program to do single imputation, you're not getting the right standard errors. So you're losing, to my mind, you're losing both the advantages. Now, for standard kinds of models, of course, the multiple imputation combining rules are built into the software. So if you're fitting like regression models, then it's really not much, no great sweat to calculate the standard errors. You have to do a bit of coding to use these things, but you have to get used to them a bit. But yeah, so I wouldn't be a big fan of that. And it might be, if you have very good predictions with the missing values, then perhaps you're not losing very much by just using one data set. But one of the big advantages of multiple imputation is you can use it even if you don't have very good predictors. You still get valid inferences. So I think there's a lot to be said for it. Since you're in the medical sciences, last week I was at Dana-Farber in Boston, so I actually gave a similar talk, except I had a bit about missing data in clinical trials, so, which is an interesting area where people are doing a lot more multiple imputation now, I think, and doing sensitivity analysis, at least in the States, and what happens in Canada. So I suspect probably similar.
Thank you.
Okay, so thank you, Grant. So Grant sent an email to everybody, but I'll send the slides to Alison, right? So maybe you could just ask Alison and she can pass them on. Would that be the best way to do? So anybody who wants a copy of the slides.
Alison, you're muted now.
That she's nodding there. So just
I'm having
give me I can send it to her now. So in that case, she'll have it essentially. So if you want to copy the slides, then bug Alison. So.
All right.
You have a great weekend.
Thank you so much.
You too.
Yes. Have a great weekend, everyone. Take care.